All right. So what I discussed with you is I'm going to repeat once again. This is the light source. As you can see, the bulb that is glowing. It is going to emit light waves, which are unpolarized ones. What is the meaning of unpolarized ones? The light waves will have the emissions being propagated in all the three dimensions, in all the volume. Now, when the light waves are made to pass through a polarimeter, a substance which has the ability to restrict the vibrations of the light in one particular single plane. Okay, then rest of the vibrations of this unpolarized light are cut out by this polarimeter, so that the light which is emitted after passing through the polarimeter will be plane polarized. What is the meaning of plane polarized light? Well, the light will be now restricted to one single plane, and you understand a laser beam or a planar light, if you have seen it before, you can relate with that, and you can understand that a plane polarized light will have its vibration only restricted to a single plane. Now, this plane of light will make an angle, let's say with x-axis. Okay, if it is making an angle of 90 degree, if you are passing this plane polarized light through an optically active organic compound or any normal compound for that matter, that plane polarized light will have its axis of vibration rotated either towards the left or towards the right. Okay, but it will rotate. It won't be same 90 degree as we are observing after just it was created when the unpolarized light was passed through the polarimeter. Okay, so this plane polarized light, which has its vibrations in one particular axis, that is like 90 degree with respect to x-axis, will be either rotated towards left or rotated towards right. If the plane of vibration of the plane polarized light is rotated by an optically active compound, the phenomenon we observed is known as optical activity. Now, what about optical isomers? See, first thing is any compound, any random compound. Let's talk about any XYZ compound. Okay, so I have an alkyl halide. Now, this is a compound. Okay, it will optical, it will show optical activity. It will rotate the plane of polarized light. So first thing is this compound is optically active, right? If I have another compound which has the same molecular formula of the given compound, so try to understand both these compounds are represented by the same molecular formula, okay, but they show difference in the axis of rotation of the plane polarized light, then they are known as enantiomers or optically active isomers. Okay, so let me just clarify what exactly I'm trying to explain here. See, after passing through the polarimeter and everything, you got a plane polarized light. Okay, what is the meaning of plane polarized light? Well, you had the light which has its vibration restricted to one single plane. Okay, so this is your plane polarized light which has its vibrations making 90 degree with respect to x-axis. Now I'm taking two compounds, okay, with the same molecular formula. I think you have a clear idea about isomerism. Isomerism is the concept where you have two or more compounds having the same molecular formula but different three-dimensional structure. And here in this case, their three-dimensional structure is also same. The only difference is in terms of their optical activity. Okay, so what about this optical activity? I have two compounds with the same molecular formula. Let's take an example for that matter. Let's say I have a compound which looks like this. I have a carbon along with OH along with CH3. Whatever the name of this compound is, you can just check it. Along with Cl and hydrogen. This is the compound. Okay. Why did I take this compound? What am I trying to convey from this compound? I'll discuss all of it later. For timing, just understand this is the compound. Now it has a three-dimensional configuration. When I say configuration, I think you should be clearly informed about what it means. And what it means is the angles these four different species are making with respect to the central carbon atom. This is the central carbon atom, right? There is no doubt in that. And there are four different groups attached to it: OH, CH3, Cl, and hydrogen. Now, all these four different groups are making a certain angle in the three dimensions. And you have to understand this also, that this compound is not on the plane of whiteboard. It is in three dimensions, right? So the angles that these four species are making with respect to the carbon is the configuration. Because of the change in configuration, okay, you will get two different optically active isomers. We'll discuss about the configuration later. For timing, just understand one compound that is the same, representing this same molecular formula, will be known as D. So what is the name of this compound? This compound is 2-chloroethane 1-ol, right? So D 2-chloroethane 1-ol is the name of one compound. Okay, and L 2-chloroethane 1-ol is the name of another compound. D 2-chloroethanol and L 2-chloroethanol. These are the two different compounds that I'm talking about. Okay, so in this box, let's assume that D 2-chloroethanol is kept, and in this box, let's assume L-chloroethanol is kept. Now, how do optically isomers behave? When this plane polarized light is made to pass through D isomer, okay, obviously it is optically active, so it is going to rotate the plane of polarized light. And when I say plane of polarized light, I think you clearly understand that the angle that it is making with respect to x-axis, that I took 90 degree over here, will be no more 90 degree. Either it is less than 90 degree or it is greater than 90 degree. Okay, so if D is rotating the plane of polarized light with respect to x-axis towards the right side, L will rotate the plane of polarized light towards the left side. Okay, it's not compulsory that D will always rotate towards right side, L will also always rotate towards left side. But according to the IUPAC sign convention, D prefix is given to those isomers which rotate the plane of polarized light towards right only. Okay, so whenever you have a D isomer, you have to be assured that it is going to rotate the plane of polarized light towards right side only. In the same way, whenever you have L isomer, you should be assured that the plane of polarized light should be rotated towards left only. So the only difference between D and L isomers is they are going to rotate the plane of polarized light. One will be rotating towards right side, the other will be rotating towards left side. And let me clarify that the angles they will be making with respect to x-axis will be exactly the same. If this is 30 degree, this has to be 30 degree. If this is 40 degree, this has to be 40 degree. That's my point. Okay, the only difference will be when D is rotating with respect to theta angle towards right, L will be rotating with respect to theta angle towards left. That's the only difference between D and L isomers. Okay, rest everything is same, molecular formula is same, configuration will be different, but you understand that the three-dimensional structure of these compounds will look exactly the same. The only thing would be different between them is that they are rotating the plane of polarized light towards right, and one is rotating towards right, which one, the D isomer, and the other one, the L isomer, will be rotating the plane of polarized light towards left. Okay, if there are two compounds, or if there are compounds which have the same molecular formula, but they are different with respect to each other in terms of the rotation of the angle or the plane of the polarized light, then these compounds are known as optically active isomers. So D 2-chloroethanol and L2-chloroethanol can be given the name of being optically active isomers. Now the next question arises, that is, how do we know that any given compound will have optically active isomer or not? Okay, so for that you have to pay attention on a concept that is known as chirality. So what is it about chirality? First of all, I would like to introduce the term of asymmetry. Okay, what is asymmetry? See, the compound that I have chosen over here, 2-chloroethanol, is an example of a compound that shows asymmetry. So what about it? Let me clarify. If you have any compound, any organic compound, since we are studying all of this in terms of organic chemistry, which has a carbon atom, okay, in the chain, like it is the carbon atom in the parent chain, and it is not compulsory that this carbon atom has to be at the first position, second position, third position, any position in the parent chain, okay, which is supposedly appearing as if it is attached with 4 different groups. And when I say 4 different groups, it's not only the atoms that should be different, it's the molecular weight. With respect to the molecular weight, these 4 groups should be different. Okay, so if there is a carbon atom in the molecule which is simultaneously attached with 4 different groups, obviously the valency of carbon is 4. Okay, and to keep our discussion simpler, I'm only talking about saturated hydrocarbons, saturated carbon compounds, which means I won't be talking about alkenes and alkynes. Okay, so I'll come back to the discussion once again, that talking only with respect to the compounds that have carbon single bond in them. Okay, if you have an organic compound where you have at least one carbon atom which is associated with completely 4 different groups, now you can see here the 4 different groups that this carbon is attached to is 1 hydrogen, 1 chlorine, 1 CH3, and 1 OH. That carbon atom will be known as chiral, and the concept of the carbon atom associating with 4 different groups is known as asymmetry. Okay, so let me just give you the basic definitions of asymmetry and chirality. So what I just discussed with you right now is that in any organic compound, if you have at least one carbon atom such that the carbon atom is attached with 4 different groups, and when I say different groups, what I mean is these groups should have different molecular weight. So let's check. What is the molecular weight of hydrogen? 1. I mean atomic weight or molecular weight, basically the unit mass. What is the mass of hydrogen? 1. What is the mass of chlorine? 35.5. What is the mass of CH3? 12 plus 3, 15. And what is the mass of OH? Oxygen 16 and hydrogen 1, then 17. All 4 are different. Okay, you should check like that, right? And if you don't want to go that complicated, you just see that they should be different. So all these 4 groups which are different, if it is attached with 4 different groups, okay, the carbon atom is called chiral.